Hey everyone, thanks for joining us for today's webinar. We'll get started here in a few minutes, and as we go along, feel free to put your questions in the chat and we'll do our best to answer all of them today.
Sponsored by Chevron Lubricants. Thank you guys so much for joining. I know that you're taking a break from work, and I know that work continues to go. But I'm excited because today is a really good topic that we're going to be discussing, and really one that may get overlooked, or in some cases, maybe a problem that you're facing right now, and you don't exactly know where to turn to, the solutions, or anything else. Today, we are going to be talking about turbine oils, and specifically more about the dark side of turbine oils being varnish, how we're going to detect it, and some proactive solutions of how to try to avoid all this in the first place. But just for those that don't know, my name is Wesley Cash. I'm the Vice President of Services here at Noria. So once again, thank you guys so much for attending. And thank you so much for those that have submitted questions in advance. I do want to say, for those that have come in, maybe you didn't get to write a question, or maybe you've thought of something since you've registered for it. By all means, go ahead and ask your questions. This is a moderated webinar, so we've got the producers and we got the folks in the back of the room here going through those, receiving them. We'll be answering questions as we can. In fact, when we finish out the education portion of this, we'll actually set aside time for question and answer. So anything that comes to mind as we're going, feel free to go ahead and put it in the chat and submit the question and everything else. But once again, thanks for showing up. So when we think about turbine oils, and I guess I should go out and say this one more time because I get busted for this from time to time. Depending on the part of the world that we're in, turbine versus turbine, just know that I use the word turbine, and we do have different types. And really, we dictate these different types based upon the fluid energy or the energy source that drives the turbine itself. And probably one of the most common turbine systems that we get into are steam turbines. We find steam turbines, absolutely everywhere. I mean, these are in, power generation. We find them in refineries, that may be driving pumps, stuff like that. Hydro turbines, we think about dams, across the United States here, the Army Corps of Engineers operates a giant fleet of hydro turbines to where we are channeling the movement of this water, right, to generate some sort of rotation. And we get this rotation that we can then couple to a generator commutator to actually make voltage and electricity, or in some cases, these turbines are coupled to a compressor. I mean, they're going to do some sort of meaningful work. Now, we also have gas turbines. So now we've got, maybe a natural gas or something that is ignited. We get this expanding gas as is ignited. That's going to power the turbine. And then we got, wind turbines, things like that. But when we think about the lubrication aspect of this, the majority of these turbines are oil lubricated. And there are many components inside the turbine systems that get lubricated. And perhaps the most important that we look at start to be the bearings of the turbine systems themselves. Most of these bearings, they are journal bearings, plain bearings, whatever we want to call them. Sleeve bearings is another name for it, where we are building a hydrodynamic film. So we actually get the shaft rotation is drawing the oil underneath it, and we float the shaft up off of the bearing surface. Well, while we generate a large film, there are several things that disrupt this film. Principally, what we worry about is contamination. So whether it be water or dirt or anything else, because bearings in journal applications like this tend to be made of very soft materials. Things like Babbitt materials. So this is going to be lead, tin, stuff like that. It's easy to wear out. So we have to worry not only about all the parameters of the turbine oil, then we have to worry about how clean it is, how cool it is, how dry it is. So we have to really focus on all these different parameters. Now, as it comes to selecting a turbine oil, a lot of people start with the base oil. Base oil, kind of the building block, if you will, of a lubricant. And they come in a variety of different flavors, if you will, right? We've got mineral base oils, we've got synthetic base oils, and depending upon the stress of the environment that we're in, really starts to dictate where some of these different base oils come in. Now, with mineral oils, these are refined, and we have certain criteria that they have to be refined to, or kind of performance criteria. And for those of you that have gone through, Noria training in the past, you start to understand there's API base oil categories, right? So the American Petroleum Institute kind of dictates them into these different groups. Group 1, has a certain level of performance that it has to meet. Group 2, even more so. Group 3, even higher. Group 4 is a PAO synthetic. Group 5, kind of all encompassing anything that doesn't fall into 1 through 4. But what we see is some of these turbines that are higher stressed, we may utilize a higher grade of the base oil. So maybe instead of, a group 1, we move to a group 2. We may use a synthetic in some cases. In fact, it's very common, for steam turbines to use a mineral oil, and they'll work perfectly fine. But we start to get into something like a gas turbine where we're running a lot hotter, maybe running at a higher speed, where we use a synthetic to kind of withstand that a little bit. Now, some of the other components or some of the other systems that may be ancillary devices to the turbine, something like an EHC system, electro-hydraulic control, not using the turbine oil, usually like a fire-resistant hydraulic. A lot of people like to lump them together, but we're going to kind of ignore that for now. We're going to talk just about the turbine system, lubricating bearings, maybe providing a seal. It could be, transmitting power in some cases, but really what we need it to do, we need it to be robust. We need it to withstand degradation. We need it to support the loads. We need it to be able to transport, contaminants out of the system, shed water. There's a lot of properties that the turbine oil has to handle. Now, some of this is dictated when we go to select a lubricant based upon the exposure that the turbine's experiencing. So if we think about a steam turbine, like I said, perhaps, at least in my experience walking through the plants, the more common of all the different turbine types being a steam turbine. Well, the most common contaminant we imagine with that is water. So whenever we select a lubricant to lubricate a steam turbine, we want to make sure that it can handle any stresses brought upon it by water. So the water can get in there, be steam leaks. I mean, it could condensate. Unfortunately, due to poor handling practice, maybe we introduce water just because we've topped it up incorrectly or something. But some of the parameters that we look at there: demulsibility, separating from water; air release. Want to make sure that we have good corrosion resistance, like rust, anti-rust or rust inhibitors. And then we think about gas turbines. Well, gas turbines run a lot hotter, a lot faster. So usually we start to look at, thermal stability quite a bit. We want to make sure that the lubricant doesn't break down rapidly in these stresses, that they can actually handle it up. And this is where, some of those synthetic bases come in. But regardless, gas, steam, hydro, I mean, there are some things that are non-negotiable. I mean, some things that we need to make sure that the oil itself can do. We need to have good oxidative stability. And oxidative stability, the ability of this oil to resist oxidation. Eventually, all oils will oxidize. Now, it's all about how well we can handle it and the different methods that we can apply to slow it down. And there are different technologies to help mitigate some of the bad things that we'll talk about. But not only do we need it to be stable in terms of oxidation, we need it to be stable in terms of viscosity, because some oils shear down over time, so the viscosity will drop. We want to make sure that our viscosity stays at an adequate level to properly lubricate these bearings. If this oil breaks down, or if we somehow change the solubility or the polarity of the oil, well, it starts to hold contaminants in a different manner, to where it may impact how filterable the oil is, or how much debris, sludge, tar, varnish, stuff that it starts to actually produce. So yes, this is very much a function of the lubricant that we have to focus on. Now, there are different standards or different classifications for turbine oil. So basically, not all oils are a turbine oil or should be considered a turbine oil. It takes a very particular type of oil to meet the standards of a turbine oil. I absolutely love grilling steaks at my house. And if you look at a T-bone and you look at a porterhouse, they're going to look very similar. And it's true, every porterhouse steak is a T-bone. But not every T-bone is a porterhouse. There are certain criteria, certain parameters that have to be met to be able to classify it that way. Our turbine oils are no different. A lot of people say, well, a turbine oil is just an R&O oil. Well, the additive signatures are similar to R&O oils, but not all R&O oils make the cut to be turbine oils. So there are different parameters, and there's a lot of different, organizations or certifying bodies that actually list parameters as to what the oil needs to be able to do to be classified as a turbine oil. Or maybe it's the manufacturer of the turbine saying the oil has to be able to withstand this type of environment or do these particular things in order for them to say this is an approved turbine oil. And some of these characteristics are chemical characteristics, some are physical characteristics. Some of them have to do with the properties like viscosity index, how much does it change, flash point, pour point. So now we got high temperature properties, low temperature properties, how well it handles contaminants. And yes, I mean, ASTM has some standards out there, different bearing manufacturers or turbine manufacturers do. And there are different, the DIN or the German Institute, the British standards. And if we started looking at some of these, here we see some typical turbine oil requirements. So we've got some GE standards, we got some ISO standards. We also have some ASTM standards. And you can see, all right, well, viscosity grades, we all understand that there's an acceptable range for viscosity grades, mins and maxes and everything else. Viscosity index based upon where it is, usually a higher viscosity index means less change in viscosity over a wide change in temperature. So it's a lot more stable. But we start looking across these and okay, they look similar. Not all have the same requirements as other, but look down here at the bottom. This is one that I want to point out that so many people overlook. Cleanliness as received. So many people think about cleanliness of the oil, once it gets into service and it's moving through the turbine, which, yes, I mean, is important, but we need to think a little bit more proactively. We need to get upstream of this a little bit, and we need to be thinking when we take receipt of a shipment of oil, it needs to meet a certain level of cleanliness. Now, our sponsor here, Chevron, they have a program known as the ISO Clean system to really guarantee a known level of cleanliness of the oil showing up. And this is fantastic, talking with your lubricant supplier to help make sure that we minimize the effort that we have to put into it to clean the oil up before it goes into service. Think about how this impacts the speed at which we can get things going. Because let's say that I ordered some oil, it showed up in bulk, and we take a sample of it. It's always a good idea to sample bulk oil showing up because cleanliness, cross-contamination, we just want to be careful because these turbines, they are very expensive pieces of equipment, and usually the downtime associated with turbines be pretty high, and that's what we're trying to avoid. So we get a bulk oil that's showing up and it's contaminated. Well, now all of a sudden we have this additional time, these additional steps of decontaminating that fluid prior to it going in service. So if we can, push the easy button, so to say, and get this oil in a manner that's more conducive to going straight into the turbine system as received, that makes it a lot easier for the mechanics, for the reliability folks, for operations, right? We want to get this thing back up and running because this is the whole key to the turbine system. With turbines, since it is a hydrodynamic film and it's a large film, anytime that we start to slow these turbines down or we have to do a lot of starts and stops, that's when we fall into what is known as boundary lubrication. This is where we have more likely, metal to metal contact. Well, turbine oils don't typically have a lot of wear control additives because the turbine should be up and running 24/7 for months, if not years on end. So once we generate that large film, we should be good to go. So it also behooves us to get rid of these contaminants because the film size really dictates how damaging these contaminants are going to be. So if we have a film size of 5 microns, well, it's the 5 micron particles that we're worried about. And so many people, I mean, they say, it's the whole clear and bright type thing. Oil sample, hold it up to the sunlight. I don't see anything in it. It's got to be clean enough. No, it's the stuff we can't see that causes more damage. So cleanliness, we got to focus on that. All right. All the other properties and parameters, very important as well. All right. But cleanliness often gets overlooked until the oil is inside the system. Then all of a sudden it's we got to filter this oil up. No, let's back that up a little. Let's make sure it's clean before it goes to the system. Now, as we start to go through here, one of the issues that plagues turbines and high speed equipment, high temperature equipment is the formation of varnish. And there's not like a single road to the formation of varnish. There's multiple roads that all kind of lead towards varnish. It's kind of like here in Tulsa where we're headquartered. There's a lot of interstates that get to Tulsa, right? It's the same destination. Well, whenever we talk about varnish, there are different sources where this varnish can actually come from. Some of it may be a hot machine surface where the varnish is physically cooked to the machine surface, or the oil, is cooked to the machine surface. Some of it can be a process that we call microdieseling. So microdieseling, we have an air bubble that's floating through this oil. And this air bubble is moving from an area where we have low pressure to an area that we have high pressure. Maybe it's through a pump or something. And if you guys remember back to chemistry, the whole ideal gas law, PV over T, right? Well, all of a sudden we're going to pressurize this air bubble. Well, the ideal gas law says as we compress or as we pressurize this air bubble and the volume, may start to change, the temperature goes way up. So now the temperature in this bubble may be superheated to where it's actually cooking the oil surrounding this bubble. Well, when that bubble finally pops, we have all these carbons and oxides and everything else that then start to float and stick to machine parts. Other things, of course, yes, if the oil is oxidized, maybe we accidentally mixed it with a different fluid that led to some sort of incompatibility. This incompatibility can lead to an increased rate of oxidation. There's electrostatic discharge, where we actually have these little microscopic lightning bolts that shoot through the oil. The oil that's in contact with those lightning bolts get cooked. But basically what we do is we are damaging the base oil molecule. And if it was a mineral oil, what we'd probably be doing is we have these hydrocarbon structures or these hydrocarbon chains, so hydrogen and carbon all bound together. Well, as this starts to oxidize, we start bolting oxygen into that hydrocarbon. So now these molecules start to get bigger. They may no longer be dissolved inside the oil. They actually get so big that the oil isn't dissolving. They become insoluble. And this is when they migrate, stick to machine parts. So a lot of this has to do with polarity of the fluid and everything else, because these oxides, they tend to be incredibly polar. Well, polar things like to stick to other polar things. I mean, think about a magnet, right? I mean, a magnet is polar. It's got two poles on it, and it's going to stick to things that also are polar. So certain metals, are more polar than others. But whenever we talk about these hydrocarbons, the base oil itself is typically nonpolar. So yes, these oxides migrate from the nonpolar base. That's why, there is a certain amount of solubility, but then they grow too big and then they stick to the machine surface. And then over time, this basically cures to a finish, to where now surfaces get gummy. Now they may get hard deposits. This can actually block flow. I mean, varnish is a big issue. I mean, varnish is something that has caused some industries to crawl forward because they can't run at the same speed. So it limits production. It limits the health of the machine. In fact, I mean, there's several different things here, right? So not only does the varnish start to build up, it says it's like almost like a fly paper, right? We got a sticky little trap here, and some of these particles start sticking to it. Well, guess what? If we have a film, film thickness, we're separating our machine parts like this, then we start to build up that gummy structure, and then we get particles stuck to it. There's a lot of added mechanical friction that we've just put between these machine surfaces. If we left it to its own devices, yes, this can generate a lot of wear, but also if this gumminess continues to pack up, now all of a sudden we may actually be having a complete closure. Now these machines can't actually move apart themselves. In my previous life working on compressors, we had a lot of compressors with heat exchangers, and we saw varnish inside of heat exchangers where basically the varnish would coat one side of the heat exchanger. And this impacted performance of the compressor because now all of a sudden we aren't able to dissipate heat from the oil nearly as effectively, because basically we put a blanket on this heat exchanger to where we don't pull the heat out of the system. So it's not just a mechanical issue in terms of frictional surfaces. There's kind of these tangential things that go on whenever we start to get varnish build up inside of our system. Now, yes, more energy consumption because they're not moving well, but also think about our filters. So if we get this varnish, build up, and maybe this varnish, breaks off or something like that, it starts to build up in our filters. Our filters plug up, blind over everything else. So now we're having to spend more time, money, effort replacing filters. So yeah, this is a big issue. And, when we start to think about varnish, it's always, well, we want to monitor varnish. We want to see, how prone our oils are to varnish, or how likely the machine is to experience varnish. And what we typically do is we call this, varnish potential testing. Because as the oil ages, as the oil is contaminated, stressed, or anything else, there becomes a point where we have a higher likelihood of varnish forming on the machine parts. So varnish potential is looking at saying, all right, well, how much of the byproducts, or maybe the precursors to varnish, exist inside the oil? And what a lot of people will use is what's known as membrane patch colorimetry, or MPC. Sometimes you hear these say, MPC values and stuff like that. This is a standardized test. And there are on-site options for this. A lot of people will employ an oil analysis lab to do this. But it says, the oil sample is aged for 72 hours. So we take the oil, and there is an aging process, to actually age this sample. And then we mix in a solvent, and then we pull it through this patch. And this is where the whole membrane patch gets its name. Now, these patches, they are a very, very fine screen, if you want to think about it like that, all right? So we have a weave of 0.45 microns, so a very, very tight screen. So as we're actually pulling the oil through this patch, it is scraping out things inside the oil that would normally not be able to be counted or be seen. Now, the patch itself is a white patch. All right, so it's completely white. And then as we're pulling these varnish precursors, or basically it's those oxides and everything else out of the oil, that patch changes color because we now have got it packed with all of these color bodies and things that were maybe dissolved inside the oil, maybe not dissolved inside the oil. But once we have that patch made, we use the spectrophotometer, and it's going to look at the density of the color. So here we got, kind of 8 different patches. And you could almost think about this as oil ages or something like that. And what we're looking at is the color density that's on this patch. How much color. And some of them break it into different, spectrums of color and everything else. But we're basically, in layman's term, how dark does the oil appear on this patch? And it's not so much the oil, I guess I should say, as much as it is the impurities or the things that have been generated. So when oil is new, this patch may not change color much at all. Here we see, the value of 2. So a low number means less color density. Now, as the oil starts to age, we're starting to see something more and more noticeable on this patch, right? By the time the oil is very aged or maybe very damaged, all of a sudden, this is a higher likelihood, or the varnish potential has gone up in this fluid. Now, remember, varnish potential is measuring kind of what's inside the oil. It doesn't mean exactly whether varnish has occurred on the machine parts or not. It's basically saying, is the environment ripe, or do the conditions exist for varnish to occur? Varnish can be very localized, meaning we have a really, really hot surface somewhere that varnish is going to be occurring and may not be seen as quickly as it diffuses through the oil. Likewise, sometimes the oil may start to degrade and we may not have varnish showing up on the machine parts yet. So just keep in mind, MPC value is very much a standard in terms of looking for varnish, but it's not always just the only way to go about it. Still, I'm a big fan of inspections. I'm still a big fan of other condition monitoring as well, to kind of look holistically how the machine is operating. And if we get the chance to do internal machine inspections, that's a great way to go about it, just to make sure that things are happening. Now, it's not that we should ever open a machine up just arbitrarily to do an inspection, but if we notice something going on, yeah, not a bad practice. So this varnish has built up inside the machine, and that's it. Now we're finished. We have to take this machine down and clean it out. Well, not necessarily. So the technology is moving forward. It is progressing to where varnish can be addressed through a variety of methods. And there are different solutions based upon type of varnish, how severe it is, everything else. A solution that's early on, are using system cleaners. So these are going to be solutions that are mixed in with the oil. And basically what this is going to do is it's going to move through the system and it's going to cut through some of the varnish. So this solution, Vartec from Chevron, does exactly that. So it's removing the varnish from the machine surface, but then it also helps stabilize the varnish inside the oil. Basically, it says a protective barrier. Think about this like, surrounding the particle and not allowing it to stick to the machine part again. So if we keep it, somewhat suspended and not allow it to stick to the machine part, we can get rid of it. So it's cutting through, it's capturing, but then it's also compatible with the in-service oil. So we don't have to remove the system from operation to put this in. The turbine can still actually operate in its normal conditions while we introduce this solution. We're cleaning up the systems, and it's okay to use temporarily. Now, keep in mind that we will change the oil eventually, because if we're experiencing a high amount of varnish, this is usually associated with some sort of damage to the base oil like we talked about. It could be oxidized or anything else. So yes, there is going to be an oil change coming up. But system cleaners, we don't have the expense of renting equipment. We may not have the expense of maybe a third party or an outside source coming in to do the labor for us. So, a system cleaner is not a bad solution to go with. Some other solutions, we've got charged particle separators. It could be electrostatic, sometimes balanced charged agglomeration. There's different methods for this. But this is playing on the fact that we mentioned earlier that these varnish particles or precursors are polar, meaning they have some sort of charge, some sort of directional affinity for other things that are polar. metal surfaces, whatever it may be. Well, with electrostatic or balanced charge agglomeration, we use these opposite charges to attract the varnish from the oil surface. So, or from the oil itself. So for instance, I mean, just very crudely, imagine that we had a layer of stacked plates, and some of these plates are positively charged, some of them are negatively charged. And we have negatively charged particles in our oil that stick to the positively charged plates. We have positive charged particles that stick to the negative or grounded plates. And over time, it builds up and the varnish adheres to them instead of the machine surface. So we remove these plates. But regardless, I mean, as we remove these particles and the oil is, robust, it can go and remove varnish from the machine surface over time. Now, we also have compressed cellulose filtration. This is usually in the reservoir. So we take like a kidney loop or something like that off of the reservoir. We pass it through a very compressed cellulose filter. So cellulose, we're thinking about, different paper type mediums. But with cellulose has a polarity to it as well. So it is actually going to pull some of the varnish out of it. And the same rules apply, all right? We do have to replace these filters and these plates and everything else. But as we remove the varnish, the oil is then cleaned up and it can go remove varnish from the system overall. And guys, whenever we talk about charged particles or compressor, I mean, this is not an immediate thing. This is kind of a long-term type thing. The system cleaners, those tend to break down the varnish that's already deposited a little bit quicker. Whenever we think about varnish that may be built up inside the machine and kind of the newest technology for this, ion exchange resins really plays on that polarity. So these ion exchange resins are engineered to where the varnish wants to bond to the resin as opposed to the machine surface. Think about it like a boat, right? On the hull of a boat, we see all these anodes because there's, the electrolysis and the attack from the seawater to the hull of the boat. The anode is the sacrificial thing. The salt water and everything wants to attack it first before it attacks the metal hull. Well, here, our ion exchange resin is that anode basically for our machine. It's the sacrificial surface area that the varnish adheres to. And then as we remove the varnish from the oil, the oil can then go through and remove the varnish from the system. So there are, several ways to address the varnish problem that we're seeing in the industry. All right, so what we're going to do is we have been collecting all the questions. Thank you guys so much. Our producer, moderator, we're going to go through them, kind of curate them. We're going to move to the question and answer session here quickly. We're going to play a short video, and then we'll be live with you with these questions.
Varnish attacks turbines from the inside, destroying performance and threatening operations. While many operators are aware of the effects of varnish, they don't realize that competitor cleaners can potentially plug system filters, cause seals to swell, and if the varnish isn't removed in a timely manner, result in the varnish being redeposited in the system. Additionally, many operators wait until the end of oil life or a critical component under performance to clean varnish from their system. There's a better way. The VarTech solution from Chevron addresses varnish in just 2 steps. Step 1, clean varnish from the system using VarTech ISC. Step 2, control future formation of varnish using a GST Advantage turbine oil formulated with VarTech technology. Competitor cleaners can cause varnish to break up in large chunks that can then plug filters. VarTech ISC outperforms competitor cleaners and does it safely by cutting through the varnish and capturing the micro-sized particles in a protective barrier within the cleaning fluid so they can be removed without overwhelming filters or redepositing onto equipment. During the months prior to your next scheduled oil change, Chevron experts will help you determine the volume and residence time needed for the system cleaner. When it's time, replace your system filters. Bleed off 10 to 20% of your reservoir capacity and add VarTech ISC system cleaner to replace the removed lubricant. Let the system return to full operation and monitor differential pressure to ensure your filters are not clogging. It's a best practice to have an extra filter set available. Once the recommended residence time is achieved, drain the used oil and cleaner mixture. Manually clean settled deposits from the reservoir and rinse the system. Then fill your newly cleaned system with a lubricant that helps prevent new varnish from forming. GST Advantage turbine oils formulated with Vartec technology are specially designed to inhibit the formation of oil degradation contaminants known as precursors, which can eventually become varnish. GST Advantage turbine oils, RO and EP, in viscosity 32 and 46 help improve oxidation stability, reduce oil degradation, and extend oil life.
All right, welcome back. So now we're going to move into the Q&A session. So we've got the producer and the moderator that have been going through. So I'm going to turn it over to Nick to ask some questions. So Nick, what do we have?
Alrighty, thanks guys. So yeah, we've got questions submitted in advance and some questions you guys have been asking in the chat. So we'll try to kind of pull the popular ones. The first one that I thought was interesting to hit, because a lot of people were kind of asking this, is varnish preventable actually in any way, or is it something we can prevent at all?
All right, so good question. Is varnish preventable? I mean, it all comes down to how well we can take care of the oil, and understand that, yes, the damage based on, or damage in the base oil is what ultimately leads to the varnish. So in terms of like a proactive approach to minimize varnish, yes, there are ways to prevent it, but you would have to be very, very in tune with what's going on. Most of the time when we teach our classes, we talk about proactive maintenance is the best approach for maintenance, because we're focusing on root causes, but it's also the one that requires the most diligence, because everyone has to be on the same page. Everyone has to be doing things correctly, because just one person doing something the wrong way undoes all this work. So let's talk about as this pertains to varnish. Well, we want to make sure that the oil is healthy. So to ensure that the oil is healthy, yes, we're going to do routine analysis to make sure that the oil is good to go. We're going to make sure that the oil's additive levels are still good. We're going to want to make sure that the oil isn't showing signs of distress. So that's kind of the analysis side of things. But now let's talk about the things that we can do to help control this. Well, to help prolong the life of the oil, cleanliness is a big manner, because there are what we call the four pro-oxidants: water, heat, air, and metal. The more contaminated our oil are, you can think about these contaminants as catalysts that ramp up the rate of oxidation, or ramp up the rate of degradation of the oil itself. So if we can keep the oil clean, cool, dry, then yes, we are going to greatly slow down the formation of any of those varnish precursors. Now, some people will go a step further and use some of the varnish mitigation strategies that we talked about as a proactive approach. So they employ them, let them run before we actually see varnish building up on machine parts. And really the goal is keeping the varnish in the soluble state. If we can keep it below the soluble state, then we never actually see varnish play down on the machine parts. But yes, it's going to require diligence. And most of the time, we're going to have to be very focused on condition control, condition monitoring, to ensure that we don't get to the environment that is conducive to put varnish on the machine. Really good question. I like that one.
Great. And then we've got one more here. This one was actually fairly popular. People asked in a lot of different ways, but the simple one is, when should turbine oil be tested?
Okay, so testing of turbine oil, when should it be tested? Probably one of the most common questions I get whenever I'm doing an oil analysis training is, well, how often do we want to test the oil? Well, oil testing, right, it is along a spectrum, if you will, of the whole cradle to grave process. So ideally, what I'd like to see, and let's say that this is a turbine system at a power plant, so this is the most critical machine at the power plant. So new oil showing up should be tested to confirm that it is clean, make sure it's defect-free, basically make sure that it is fit for service. So I want to test new oil first before it goes into service. Now, if we have oil that's been stored for a significant amount of time, let's say that we've got oil that's been stored for 6 months, a year, something like that, I want to test that before it goes into service. So this is all kind of upstream of once it gets into the machine. Now, once it gets into the machine, which I think is probably where this question ultimately lies, is saying, while the oil is in service, how often should it be tested? And some people say, well, we want to test it, quarterly, semi-annually. I try to shoot for, if we don't have a good kind of backlog of data of how this machine is running, I want to start sampling it at least monthly. These big systems like this, the critical systems, we want to start to generate a trend of how the machine is actually operating. And if we start sampling it monthly and we get, 3-4 months behind us and we start to see, all right, well, we are consistently well below our margins in terms of cleanliness, meaning it's much cleaner, maybe it's much drier than what we need it to be. And maybe our oil is very healthy. Well, then maybe we dial it off to every 2 months. But if we start doing that monthly sampling, we find that we are butted up against the actual target, or maybe even exceeding it in terms of it's dirtier, it's wetter, or maybe we're starting to show signs of oxidation or acid numbers increasing, then we may want to ramp it up to every couple of weeks, because that's signaling to me that we have some level of distress. If you wanted a clean round number, right, I'm going to say once a month starting out. Let's go once a month to get the data that we need. From there, either increase or decrease based upon the results that we're seeing from the analysis. I mean, some turbine manufacturers will say, sample every 500 running hours. Well, a month, I mean, if we extrapolate it across the year, a month is somewhere around like 750 hours. So that'd be what, every 3 weeks or a little bit more. So, I mean, even some manufacturers, put you right around that monthly mark. So that'd be a good place to start.
Great. And so one more that we've got that's, this is dealing with PAGs. So describe why PAGs are more resistant to varnish formation compared to other base oils.
Okay, so PAGs, polyalkylene glycols, why are they more resistant to varnish than other oils? Interesting question, right? PAGs, polyalkylene glycols, are kind of gaining in prominence for use in a lot of different applications. Turbines, no exception, especially gas turbines. You're starting to see a lot of PAGs and gas turbines. And one thing that we need to know about PAGs, all right, unlike a Group 1 mineral oil, all right, a Group 1 mineral oil has a certain level of performance, right, that it has to meet to be classified as a Group 1. Well, PAGs are formulated in different ratios or different building blocks based upon PAGs that may be ethylene oxide versus propylene oxide and any blend in between there. And the difference here is some PAGs are completely soluble in water, some PAGs are completely soluble in oil, and then anywhere in between those. Well, when we talk about PAGs being, sometimes they are touted as a non-varnishing or maybe even a varnish removal type system, it all comes down to the chemistry of the PAG molecule itself. Many of these PAG molecules tend to be a more polar molecule. So unlike the mineral oils that we talked about in the earlier session here, being non-polar, so the polar oxides and stuff want to leave the oil and stick to the machine part. Well, if the PAG is polar, then the oxides and everything else are almost more prone to get dissolved inside the PAG than it is to leave and stick to the machine. So you can think about the PAG as almost having a higher capacity to dissolve the varnish. And it's all because of this polarity. So they kind of stay more tightly compacted. They stay mixed in with the oil as opposed to leaving it, leading to the varnish. But yes, I mean, PAGs are used in a wide variety of turbine applications because of that. Sometimes they have better oxidative resistance because it being a synthetic, just being a little bit more robust in some cases. But a lot of people like that whole kind of resistance to varnish or a lower tendency to varnish, but it comes down to polarity. Good question.
Great. And one more we've got here is at what point, and I'm not even sure what sweetening is in this context, at what point does sweetening become counterproductive compared to cleaning and change out? Can you tell us about that?
So sweetening the oil, all right, at what point does sweetening become counterproductive to changing? And sweetening, all right, so slang word, is used quite a bit. What we're doing is when we sweeten the oil, we're doing a partial change, or sometimes called a bleed and feed, meaning, all right, we've got this turbine reservoir and whole numbers. This holds 1,000 gallons. Maybe we drain 100 gallons out and we put 100 gallons of new fresh oil in on top of it. This is sweetening the oil because the new oil brings in it new additives. It's a healthier base oil. But when is it counterproductive to sweeten versus a change out? And it's a good question. I like it because I've worked with many organizations asking this exact same question. Because let's be honest, if we have thousands of gallons of oil that we're having to change, I mean, that does represent an outlaying of capital. We also may have to take the machine down. So now all of a sudden we have lost production or anything else associated with the machine not running. So some people want to extend that out as long as possible. Now, when does sweetening make sense? Well, sweetening makes sense when the base oil is still healthy. We don't see a lot of damage in the base oil or anything like that. And bringing in the new oil will help kind of enhance or get it back to a like new state to where it's good to go. It makes sense whenever we're trying to just extend the drain interval by maybe a couple months, not indefinitely, right? That's when sweetening really works. It's counterproductive when all we're doing is just trying to do a partial change in hopes that this oil charge is going to last forever. Because the issue here lies with the actual base oil molecules itself. Let's say that we go to my fridge in my house, and in there I've got a Tupperware full of grapes. All right. And some of these grapes are still perfectly happy and healthy. Some of these grapes are decaying and rot and everything else. And I say, all right, well, we're going to swap out some of these grapes with new grapes. But you are blindly picking out the grapes out of this Tupperware. So you're going to remove some of the damaged ones. You're going to remove some of the good ones. And we're going to put all these fresh good ones on top of it. Well, the issue is those old decaying grapes make the new grapes go bad even faster. Well, the same is true with our oil. So our oil, when people go to sweeten it, it's because maybe we're having demulsibility problems or aeration problems. So we've got an infection inside that oil. And instead of treating the infection, what we're doing is we're just kind of, heaping this new oil on top of it, hoping that we dilute it enough. Well, what tends to happen is the new oil is actually going to become infected, and we're actually not going to see as big of an improvement as we may once imagine. So when it's counterproductive is when the base oil itself is damaged. And all we're doing is trying to attempt to restore the base oil's health. Sweetening is not going to help in those cases. Really good question.
Great. We've got one more that's this one's very general, but I think it's something I'm seeing a theme of in a lot of the questions. Can we talk a little bit more about just cleanliness and kind of what goes into really keeping your turbine oil clean enough or even proactively clean?
All right. So cleanliness in general, or I love the way you phrased it there, Nick. Clean enough. That's all right. So what goes into this? And I'm sure I sound like a broken record at this point, but cleanliness begins, right, whenever we take custody of this. And this is where most people's, what would you say, maybe authority ends, is when the oil actually shows up. So we want to make sure that when we receive the oil that it is clean. So this is decontamination of the oil. Now, if we use an ISO clean system or something like that, where the supplier is doing some of this makes it a lot easier as it shows up. But in terms of cleanliness, we are usually going to make sure that we're using a good beta rated filter, meaning that we've got a high capture efficiency. And capture efficiency is all going to be based upon how many times does this filter get the chance to see the oil. If this oil is sitting in a tote somewhere, or maybe it's sitting in a drum somewhere, and we get the chance to circulate this oil through the filter multiple times, we can get away with a lower efficiency filter because the oil is going to see that filter, who knows, a couple hundred times before it actually goes into service. But what a lot of people do is they want to filter it once, and they're going to suck it from the drum through a filter into the reservoir. At that point, it needs to be the most efficient filter that we can, because that oil got one shot. That filter sees the oil one time to remove as many of those contaminants as possible. So that's where we want to do it. Now, of course, you size your filters accordingly as well. Turbine oils, it's not uncommon to see a 3-micron beta 1000 filter or something in use to make sure that we are scrubbing the small contaminants, because it's the stuff below what we can see. It's usually the 10 micron and less particles that cause the most damage. So in terms of cleanliness, right, we want to focus really on filtration. It's got two sides to this. Any contamination control program should look at excluding particles as well as removing particles. And excluding particles is how well the system is set up to reduce the ingression. Now, the ingression of particles, they can be from the atmosphere. All right, so this is what we call ingested, right? They're brought in from the environment around. They are built in, meaning machine parts, like how clean is the machine part, or maybe this system was opened up to do some sort of maintenance and we didn't cap hoses or anything else. So now all this stuff came into it. And then some of them are generated. This is wear debris and things like that. So on the exclusion side, we want to make sure that we're using the right oil to minimize any wear debris. We want to make sure that the system is in a hermetic state the best that we possibly can. So good breathers, good seals. As we're doing our maintenance, that it stays in that hermetic state. So the use of quick connect fittings, making sure that the new oil as it's applied is done so in a clean manner. Now on the removal side, yes, this is filtration. It's the best tool in our arsenal. And we look at the different places that we can filter the oil. Supply lines, return lines, kidney loops. We want to optimize our filter selection for those cases. So really good question, but yeah, I mean, we focus on cleanliness.
Yes, got it. And there it's also kind of related to what you were just saying about, filtration. Somebody asked, is a depth filter a suitable solution for varnish removal?
All right, depth filtration is fantastic for contaminant removal. Is it suitable for varnish removal? Yes. I mean, depth will remove some of the varnish as it gets built up into the oil. And depth media really focuses on the stuff that's more insoluble, meaning the varnish precursors that are likely to stick to the surfaces. It may have some constraints in terms of removing the stuff that is actually soluble in the oil. So, is it something that I would just hang my hat on solely on? Maybe not if we're having an extended varnish issue, but it is a great system to remove that over time, but it also works really great with solid particles. So it's not to downplay it. It's just we want to make sure that it's right for the application. So without understanding exactly what we're talking about, if we're not seeing a lot of varnish buildup and we put in a compressed cellulose depth media, then yeah, I mean, I wouldn't have any reservations that it wouldn't be able to keep up or help minimize that. But if we have something with, already, hard deposits, it may be a lot longer and it may be a lot harder for that technology to kind of catch up and remove that. I mean, maybe use that in relationship to one of those system boosters like the Vartech or something like that.
All righty. I think we've got time for one last question here. And kind of ties in maybe a little bit to what you were just saying, but is it possible to add additives, and they put in parentheses antioxidant, back to oil, which has had its varnish levels, MPC number, they put in parentheses, reduced by filtration?
All right, so is it possible to basically re-additize the oil? The straight answer is yes. All right, it can happen, but there are very, very specific ways that we would want to make sure that this is done. It's not as simple as just going and buying the antioxidant, throwing it down in the reservoir and saying we're good to go. We do want to make sure that the base oil is healthy, because if the base oil is damaged, I mean, think back to what we were talking about sweetening just a little bit ago. If the base oil is damaged, no amount of antioxidants that you throw in there is going to help out. I mean, at that point, we're on borrowed time for that oil to be changed out. Now, if our base oil is healthy and we are just seeing a normal depletion of the antioxidants, then yes, it may be possible. Now, what we have to do is we do want to get our suppliers involved. We want to kind of mix this in a lab environment to see if the oil can actually intake the antioxidants. We want to make sure that it's as similar of a package as we begin with as possible. And then if it is compatible, let's say that they are compatible, that it actually can be blended back in, we do want to introduce this into the environment in a manner that we have a little bit of turbulence to get it mixed up and blended and kind of homogenized throughout the system. So the straight answer is yes, oils can be re-additized. In fact, there's this whole movement now, right, to think about oil as simply a conduit. The oil itself is what's transporting the additives to the surfaces to do the work. It's what's transporting contaminants to the filter to clean it up. So yes, the oil should be able to get some of these additives back in it. Now, like I said, there are confines, and here's the issue, right? When it comes to risky, I have seen people rely more on just trying to re-additize a fluid than truly addressing the root cause of what may be going on, what's causing the damage. So if we have fixed what may be causing the damage of the oil and it's in a good state, then yeah, reanodization may work. If we're just doing this in hopes to delay changing it out, I wouldn't recommend. So good question. So Nick, I do appreciate the questions. I appreciate all you guys putting in questions and submitting them. Unfortunately, we're running low on time here, so we're going to have to call it. I mean, if we didn't get to your question here on air, we will be following up. Maybe this sparked other questions. By all means, put those questions in here. You will see a couple of links to different solutions related to cleanliness, related to varnish. So please check them out. And please, join us again for our next webinar in these series as we're going through. And we definitely look forward to that. So you guys take care.
Hey everyone, hope you all enjoyed today's webinar. If you want to get insights into the type of varnish that you might have, scan this QR code with your phone or click the link that's been added to the chat to request a free MPC Plus oil sampling kit and analysis from Chevron. Thanks again for joining and have a great day.
Hi, everyone. This is Josh, the producer. I'm going to go ahead and turn this webinar off. So if you haven't had a chance to submit your questions, I'll throw an email for one of our employees here in the chat so that you can reach directly out to us, or you can reach out to Chevron as well. Thanks again for attending, everybody.